Welcome, curious minds, to another deep dive. Today, we're tackling the atom. Yeah, the fundamental building block of, well, everything. We're using Andrea Mini's notes as our guide to really get inside these tiny particles.
That's the plan. We want to break down the atom, look at its core parts, and figure out how they dictate the properties of everything around us.
Okay, let's jump in. So Mini points out right away, an atom isn't just a single thing. It's got two main zones. There's a central core that's positive, and then these negative bits electrons kind of orbiting around it.
Precisely. And the scale difference here is pretty staggering. That central nucleus, it's incredibly tiny compared to the whole atom. Mini uses a fantastic analogy. Think of the nucleus as a single glass marble sitting right in the middle of a soccer field.
A marble in a whole soccer field.
Yeah, and the entire field represents the atom itself.
Wow. So the rest of that field, most of the atom, is just empty space.
Pretty much. But it's kind of mind-boggling when you think about solid objects being mostly nothing.
Makes you almost feel like you could fall through your chair. So what is inside that tiny marble? The nucleus.
Right. Inside the nucleus, you've got positive particles, those are the protons, and also neutral ones, the neutrons.
Yeah.
And orbiting way out, like you said, are the negatively charged electrons.
Okay, and the protons seem really important. Mini stresses their number, the atomic number. Z is like the element's ID card, right? Hydrogen always has one proton, carbon always 6, oxygen 8. You change that number.
And you change the element entirely. Absolutely. It's the fundamental fingerprint.
Got it. And for a normal neutral atom, the number of electrons matches the number of protons.
Exactly. The negative electrons perfectly balance the positive protons. Electrically neutral.
Okay, so protons define the element. What about the neutrons then? If they're neutral, what's their big role?
Good question. Well, neutrons, along with the protons, they determine the atom's mass. You add protons, Z, and neutrons, N, to get the mass number A. But maybe even more importantly, neutrons play a huge role in nuclear stability, keeping that tiny nucleus from flying apart.
Stability. So that's how we get different versions of the same element, isotopes. Is that the idea?
That's exactly it. You've got it. Same number of protons, so it's the same element, but a different number of neutrons. Like hydrogen, usually no neutrons, but add 1, it's deuterium, add 2, it's tritium. Still hydrogen, but different mass, different properties.
Or like carbon-12 versus carbon-14.
Perfect example. Carbon-12. 6 protons, 6 neutrons stable. Carbon-14. 6 protons, but 8 neutrons. That makes it unstable, radioactive. It's the one we use for carbon dating, you know.
Fascinating. Okay, so protons change the element, neutrons make isotopes. Well, what if the electron count changes compared to the protons?
Then the atom isn't neutral anymore. It becomes an ion, it has a net charge. If it loses an electron, the positive protons outnumber the negative electrons, so it becomes a positive ion. We call that a cation. Think Na plus air, sodium ion.
Cation, positive, got it.
And if it gains an electron, it has extra negative charge. It's a negative ion or an anion. Oxygen often does this, grabbing electrons to become O-rin.
Anion, negative. Okay, so these electrons, you said they orbit, but it's not like planets around the sun, is it? How are they actually arranged?
No, not quite like planets. It's more about probabilities.
Yeah.
They exist in specific regions of space called orbitals. Think of them as zones where you're most likely to find an electron.
Orbitals, right, like S, P, D, F. I remember those letters.
Exactly those. And each type has a distinct shape. S orbitals are spherical, just like a ball. P orbitals look more like, well, like 2 lobes, sort of a dumbbell shape. Each single orbital, whatever its shape, can hold a maximum of 2 electrons. And these orbitals are grouped into energy levels, or shells, further and further from the nucleus. It gets a bit complex sometimes. An orbital in a higher shell might actually fill up before one in a lower shell, like 4s before 3rd. Quantum mechanics gets weird.
Ah, sounds like it.
But here's the really crucial takeaway. The arrangement of the outermost electrons, the electronic configuration, that dictates almost everything about how an atom behaves chemically, how it bonds with other atoms, what kind of molecules it forms. It all comes down to those outer electrons.
Right. So, wrapping up Minnie's points, tiny, dense, positive nucleus with protons and neutrons. Electrons orbiting in these specific probability zones, these orbitals, are mostly empty space. Protons set the element. Neutrons affect mass and stability, giving us isotopes. Electron count makes ions, and electron arrangement drives chemistry.
You've nailed it. That's the core picture. The structure, the particles, how their numbers and arrangement dictate stability, reactivity, basically everything. It's still amazing to think about solid matter being mostly empty and the sheer forces holding that tiny nucleus together.
It really is. Which leaves us with a thought to chew on. If atoms are mostly empty space and particles are just probabilities, What does it actually mean when we touch something? What is that feeling of solidity? Something to ponder until our next deep dive.